What we're going to start with is actually looking at the reduction reagents real quickly. So if you guys remember our reduction reagents, we really had three primary ones when we're looking at our carbonyls. We could add a fourth in there, and actually we could potentially add a fifth. Do you guys remember any of those others? Sixth. So diball works. Anybody remember some of the other ones? A very common one is the NH2 followed by KOH in heat. That is a pretty popular one as far as the ACS exam goes, so you should be aware of that one.
Which one? The bottom one?
E, currently E. It's a little bit different as far as its reducing ability because it'll take your carbonyl all the way down to an alkane. So it fully reduces. Another reducing agent? chm236 is an oxidizing agent. You might see the zinc, mercury, and HCl. I've seen this one show up all over the place. Pretty much if I were you when taking a test, if I saw pretty much any metal with HCl, just reduce. And it typically takes it down to an alkane as well. Right. And that's just because there's a ton of them. Tin will do it. Zinc and mercury is the common one that we've seen pop up in the slides every so often. But it'll do the same thing, full reduction down. And diball is a controlled reduction. So we can add that information here too. So yeah, controlled. It doesn't necessarily mean to an aldehyde. It means we can stop at an aldehyde if we wanted to. Okay, so it's a controlled reduction. Whereas the lithium aluminum hydride and the sodium borohydride aren't controlled. Yep. So let's clear all that away again and kind of get to the point of where the slide was actually trying to get to, but I didn't have the proper figure, between sodium borohydride and lithium aluminum hydride. What was our difference? I'm game. What is it? And esters and carboxylic acids. Okay, why? We may not need to get into the why necessarily, but maybe you remember. Both of those reagents supply what nucleophile? Hydride, H-. So you're looking at a super reactive structure that should immediately go in and react with an electrophile as quickly as possible. Okay? But in the case of sodium borohydride, those hydrides are temporarily or more permanently stabilized by the sodium and the boron, that those hydride nucleophiles are not as nucleophilic, which means when we move to an ester or a carboxylic acid, where we've minimized the electrophilic character of those functional groups, sodium borohydride can't do that attack. Okay? We said there was kind of that arbitrary limit, or what appeared to be arbitrary for us. There's this line where we say, line in the sand, sodium borohydride can only deal with our ketones and aldehydes. And the opposite end of that sand, our lithium aluminum hydride is more reactive and can go through and take out a bunch of other functional groups as well. Okay? So we talked about that, we've got that line. Well, now what we're going to do is introduce a new line. Okay? And a lot of people have been having questions about this, both from the ACS exam and from exam 3 as well. Looking at reversible reactions. So pretty much everything within this last exam had some reversible characteristics. So let's look at the general idea first. What determines whether an addition is going to be reversible or not? So we got a nice little reaction there for us. How can we decide if that reaction is going to be reversible? Right? We could start to do some evaluation of stability of the ketone.
How reactive the product
Okay.
is.
And how reactive the product is. What I would argue we should do is the same kind of thing that we did with acids and bases on deciding which side of our reaction decides to give up a hydrogen. Right? Which one acts as the acid or the base. And we can look at pKa's. The one with the smaller pKa is the stronger acid. It goes away from that. It was a way of quantifying our reactivity. Right? And to do that, we had to look at our acids and know something about our pKa's. One of the things that we keep talking about this semester is that when you see a reaction, the first thing that you should zero in on would be what? Could look at change. Let's say you were just given reactants. We cross out all the products so you can't see those. We can't look at what changes because now you don't have anything of what it changed into. What would you look for? Most reactive thing. What makes it most reactive? Charges. Right? So one thing we could go through and do is evaluate something about the charges. Right? We could look at our nucleophile having a negative charge and compare that to our product where the oxygen has a negative charge. So if we drop in, say, sodium borohydride with H-, would we expect sodium borohydride to be a reversible reaction?
Yes.
Which atom would rather hold the negative charge, hydrogen or oxygen? Is that a close comparison or not at all?
No.
Not at all. Okay. So it's not a question of can it still happen. It's a question of in comparison to something else, is it likely to happen? H- is very unstable. Right? I don't think we've even looked at a reaction so far this semester where we've generated H- in a reaction. We've added it, okay, but we've never generated it. Why not? It's incredibly unstable. Why is it incredibly unstable? We can look at the size of hydrogen. It's tiny, so it can't stabilize that negative charge. What else? Low electronegativity. It's not willing to even hold the electrons. Okay? So if we looked at the hydride reaction, we might expect that that reaction is not going to be reversible because I'm moving towards a negative oxygen. And what's special about the negative oxygen? Comparison to hydrogen, what's its size? It's much larger. Comparison to electronegativity? Much more electronegative. So if we look at our reactivity back to this idea of charges and always trying to stabilize the charge, we would expect this reaction to not be reversible because I want to take it to that most stable negative charge as possible, which is going to be that oxygen. All right, so it's a question of finding that balance. What happens if we switch it up to a Grignard nucleophile? Okay, let's go ahead and leave our H- here, and we said not reversible. What happens if we switch that to a Grignard nucleophile? What would I draw as my symbol for my nucleophile? All right, at its simplest level, we'll just look at a negative carbon. Okay, officially, yeah, we'd add the MgBr and all that fun stuff, but ultimately all we're looking at is a negative carbon. And we look at this now going to, again, our oxygen as a negative. Which atom would rather hold that negative charge? The oxygen. So how would we expect this reaction to go? Should favor the products. Okay? Now we come in with the questions that you would see on a multiple choice exam. Which of these would favor the products less? Okay. It's a tricky question. So said another way, what we're asking is which of these is a reversible reaction? We just said both of them are non-reversible. But it's a comparison. I don't care that it's non-reversible. I'm saying in comparison to the other one, is it more or less reversible? Okay? So when we look at this, we're now trying to compare those two reactions. What should we compare between those? The reactants or the products? Why the reactants? Products are exactly the same. So focus on the difference. Which atom would rather hold a negative charge? Carbon or hydrogen? Which means what about the reversibility of our second reaction? It is more reversible than the other one. Does that make it a reversible reaction? Not necessarily. Right? It's a comparison. It is more reversible than this other option. Right? We could continue to go through and do this. We could look at enolates. When we look at the enolate, what's our nucleophile? It's kind of a tricky one.
It could be the oxygen or the hydrogen.
Oxygen or the carbon, what did we see the enolate act as? Which was our reactive atom? It was the carbon. It's a carbon nucleophile again. Okay? And if we drew that one out, we could just draw the exact same thing as we had already with another carbon nucleophile, except is that going to help us do our comparison? Why not? It's the same as the previous one. So instead of looking at it just as a carbon, what can we do to tweak that structure a little bit? We could show more of what makes it an enolate. What makes it an enolate? Carbonyl, right? So now when we go through and try and compare, which of these would we expect to be more reversible? The enolate or our Grignard? Why? There is resonance stabilization, which causes our enolate to be a little bit more stable. So it's a little bit more reversible than our Grignard reagent. Okay, so we're looking at these raw thresholds and saying, in these comparisons, how does this end up working out? Okay, kind of makes sense? What if we dropped in the cyanide, which unfortunately I put in the wrong order? Compare the cyanide to our Grignard reagent. What's the nucleophile? Still C minus. It's our carbon again. Okay. C minus to C minus. Does that help? No? So what do we have to do? Draw more information out of this. Within that, what do we see? See a nitrogen. What is that going to do to that negative charge? Make it even more stable, because it's now going to start to draw those electron or that electron density into the bond structure between the carbon and the nitrogen, because nitrogen is more electronegative than the carbon. What is that going to do to the reversibility? It's going to increase reversibility, because now we can stabilize that negative charge. Okay? So in all of these cases, what we're looking at is how reactive is that negative. And at a certain point, we can start to see that there's a lot of reversibility coming out of it. Okay? That reversibility becomes very, very important when we talk about the idea of this last one, our alkyl cuprates, okay? Also known as our Gilman reagents. Okay? Because they run very relatively reversible reactions, that's going to change their preference for how they go through and react. Okay? So in the case of our alkyl cuprates, what we end up doing, I guess, sorry, were there questions on that? I apologize. Okay, when we move to the alkyl cuprates, what's happening now? Well, we'll take a carbon lithium compound. Okay, what charge would that carbon be? Negative. How do you know the carbon is negative in a carbon lithium compound? Why is lithium positive? All of our metals pick up a positive charge, which means our carbon is negative. When we mix this with a copper halide solution or a copper halide compound, what ends up happening is sort of an effective substitution reaction. and we end up substituting our carbon for the bromide. Why might we do that? Why would that reaction progress forwards? So ignore that part for the moment.
Can you repeat that?
Why would we expect that reaction to progress forwards? If we look at our charges, we're saying bromine is negative, our lithium stayed positive the whole time. Why would our reaction progress forwards? Bromine, being a negative charge, is much more stable than a carbon with a negative charge. Right? So the carbon will displace the bromine in that copper compound. Right? So we're trying to do some predictions and guesswork based on those charges and those stabilities to try and come up with some way to explain what we're seeing. In solution, what ends up happening is we react a second equivalent. A second equivalent of our organolithium compound. And what ends up happening is our negatively charged carbon will go through and directly link up with our copper and form this fancy looking anion at the far end. Okay. This has some interesting features. What type of bond do we have between the carbon and our copper? It's an ionic bond. What charge is our R group? It's negatively charged. Okay. Our R group is now a nucleophile. What happened to its overall nucleophilicity, or sorry, its negative character? Did it increase, become more negative, or less negative in the course of this reaction?
Is the which became copper also negative?
The overall complex is negatively charged. Okay. Because of how those groups are attached, the copper picks up a formal charge of a -1, much the same way if we looked at sodium borohydride. Where's the negative charge in sodium borohydride? It's on the boron, but how does sodium borohydride react? As a hydride nucleophile. Okay? Same kind of things happening here with our copper reagent. So we evaluate that R group, more or less negative. Heard a same. If it's the same, what had to happen? That bond with carbon was replaced with something of equal electronegativity. Is there an equal electronegativity between lithium and copper? No. So it's definitely changed. Which one do you think is more electronegative? Copper. Why? Farther to the right on our periodic table, getting closer to our electronegative element, fluorine. Well, if copper's electronegativity is increased relative to lithium, what did that do to the charge on our carbon? We could say more positive. It's a little bit odd of a phrase to say because it is still negative. So I would use the opposite terminology, which was less negative. Okay? You're both saying the same thing, just from slightly different perspectives. Okay? So our carbon has now become less negative, which does what to its nucleophilic character? It's less nucleophilic. Okay? Our alkyl lithium reagents almost always act exclusively as, anybody remember? Very often they go through and act as bases, okay, because that bond is exceptionally weak or exceptionally polarized between the carbon and the lithium. We've now increased some electron density in that bond, and we've ended up generating a better nucleophile. Organic lithium compounds can act as nucleophiles. Don't get me completely wrong on that. They're just so negative that very rarely are they actually stabilized long enough to get into a nucleophilic site, okay, or an electrophilic site. So we've now converted our carbon from being effectively a base to now potentially being a nucleophile. Okay? So what this copper ion does is it kind of catalyzes or acts as a catalyst to reduce the reactivity of our carbon down into something that can actually be useful. I can now connect it to something other than hydrogen. Okay? So this is something that you will see in a lot of the ACS questions, in my opinion. They like to throw in these coupling reagents. Okay? Most of the reagents they throw in there are things that we've never talked about. Okay? That's because they're current research. But what they do give you access to is some information about how those reagents work. The metal ion is there just to facilitate the transfer of one positive to one negative. Okay? That's all they're trying to do. So if you can identify the positive and the negative, who cares what metal catalyst it is? All the metal catalyst is going to do is get those two atoms near each other so they can form a bond. That bond can also be referred to as a coupling, because we put two things together. Okay? Your copper reagents or your alkyl cuprates are doing effectively this. Okay? They're coupling agents. They're going to link two carbon structures with each other. Okay? So, in general, we could use them to do pretty much anything that we had an electrophile for. Okay? But where these become a little bit more relevant comes back to what we've been looking at, our aldol chemistry. And if we looked at an aldol reaction, if we did this condensation, we end up with that product. What's the name of that product? Alpha, beta, unsaturated. What's that last functional group? It's an aldehyde. So we have an alpha, beta, unsaturated aldehyde. Okay, when you look at that functional group, this is something that you should be keying in on. Okay, you should look at that and say, oh, it has this reactivity. So what reactivity do you see in that structure? In the product. Right, we can switch it back to the reactant. We're seeing some hesitancy. What reactivity do you see in the reactant? We have an electrophilic carbon. What else do we have? Where's that acidic hydrogen? On our alpha carbon, we have an acidic hydrogen. What else do we see? Okay, we've got a basic oxygen. See anything else? Pretty much the end of it. If we pulled off that acidic hydrogen, then what would we have? Then we could have a nucleophilic carbon. Okay, so what we're doing is trying to identify sites of reactivity. If we can find a positive and a negative, we can come up with a prediction on how it might interact with something else. So if we go through and look at the product, can we do the same thing? Yes. What things have not changed? We have a basic oxygen. What else do we have? We've got that electrophilic carbon. Do we have an acidic hydrogen? There is a hydrogen there. Is it acidic? No. Our hydrogen was acidic initially because of resonance stabilization. If we pull this hydrogen off, we actually disrupt the resonance of this pi bond with the carbonyl. Okay, so that hydrogen is not acidic anymore. The one I now just erased. Okay, we do have an alpha hydrogen. That alpha hydrogen is not acidic.
Why not?
Okay. If we look at our structure, we have a resonance overlap of the pi bonds with each other. If we pull the hydrogen off, for it to be pulled off, it must be resonance stabilized. If we pull that hydrogen off so that it can then do resonance, the only way it would be able to do resonance is with our carbonyl. But as soon as we attempt to do that, what happens? We rotate the pi system, our double bond, out of resonance. Okay? So we start with a structure that has resonance. We try and remove the hydrogen, and then we disrupt that very same resonance that made it stable to begin with. I'm seeing some questionable looks. This is something that is incredibly hard to draw. I'm not sure I'm going to be able to pull this off, but we'll try it. Okay, we've made reference to it a couple times before. Pi system. Alpha carbon, carbonyl carbon. Right? If we've got resonance, those p orbitals overlap with each other. Right? So since they're now in an overlapping situation, right, they can do resonance with each other. If we now look at the hydrogen, when I say this with alpha, we look at the hydrogen, where is the hydrogen relative to that pi system? It is perpendicular to that axis. Okay. How do we know this? It goes all the way back to chapter 1 and 2 when we talked about hybridization and what's happening within each of those bond structures. That hydrogen is orthogonal to this pi system. Okay. So we said we had a nice stable pi system because we got overlapping p orbitals. If we take a look at that hydrogen and we take those electrons and I want to do resonance, what do I have to do? I have to get those electrons to overlap my pi system. I cannot get them to overlap with my p, or my purple pen in this case, because they're attached to the same carbon. Okay? I can't take two p orbitals on the same atom and overlap them. It doesn't work. Okay? They will always be orthogonal to each other. So what I have to go through and do to get those red electrons, or hydrogen electrons, to form some kind of resonance stabilization would be to rotate it. But as soon as I rotate it, what happens to the pi bond I had? I now have no overlap and I've destroyed my structure, or I've destroyed that resonance stabilization. Okay? So what driving force is there to remove that hydrogen if the very first thing I'm going to do is now get rid of resonance? No driving force. Which means not acidic. Okay? What else do you see? As a hint. This orange structure, what do you see there? What's reactive about that? Pi bond. What does the pi bond act as? Source of electrons. We got a nucleophile, potentially a base. Take that same information that we now know about that up to our new structure, this alpha beta unsaturated aldehyde. What happens? We might try and say that pi bond is a nucleophile. There's an issue with that pi bond. What's that issue? Is that pi bond a good nucleophile? Why not? Resonance stabilized. Those electrons are involved in resonance with the carbonyl oxygen. Right? That nullifies the reactivity of that pi bond. So if we compare nucleophilic characteristics, the pi bond in our alpha beta unsaturated aldehyde is not nucleophilic. A standard alkene is. The alkene is nucleophilic because those electrons are localized to that position. They have nowhere else to go. As soon as we throw in resonance, we've now reduced the nucleophilic character. Okay? So if that can't act as a nucleophile, then are we done? How do you know it's an electrophile? There's electrons there. What I believe you're asking me to do is to draw a resonance structure. When we draw that resonance structure, what do we get? What's that? You can get an enolate and positively charged carbon. This is something I'm seeing a lot of people miss. If you're going to show resonance, that's good. Add some arrows into it. Make sure every single arrow is explained in your final product. We took electrons from that pi bond and moved it into a new carbon-carbon bond. Right? The result is that our carbon lost electrons. It must become positively charged. What is the relationship between these two structures? Resonance. Are they tautomers? This is a tricky question. No. To be tautomers, what has to happen? You need to remove a hydrogen. We have not touched any sigma bonds in the formation of this. This is strictly resonance. Yes, we have formed an enolate, but that enolate is not a tautomer of what we started with. Okay? So we have to be careful with those definitions. The result of all of this is that what did I end up finding? Another electrophilic atom. Okay? Why is this problematic? Well, what was the previous slide talking about? We looked at what? What was reversible? Reversible.
The reaction is the product.
What reaction? What type of addition? Nucleophilic addition to carbonyls. In this situation, we have a carbonyl. Okay? So if we clean this up, any questions about what's up there? Can I erase everything? Okay, it's all getting erased. We have an electrophilic carbon, and we have an electrophilic carbon. If I now add a nucleophile, where does that that nucleophilic carbon go? That's going to be problematic. We have to have something to decide, some way to say it's going to go either to the beta position or go to the carbonyl carbon. Well, how do we know where it goes?
Experiment.
Kind of. Has to do with that reversibility aspect, which is why we talked about reversibility. If we've got a structure that is incredibly unstable, so I add in a Grignard reagent, an sp3 carbon, cH3MgBr. How stable is that Grignard? Not stable at all. Okay? We expose that to just air, what happens? We kill the Grignard. It reacts instantly with air. Okay? Extremely unstable. So what is that extremely unstable negative going to want to try and do? Find a positive. We've got two positives to choose from. Which one does it choose? Okay? The one with the bigger positive. Which one's the bigger positive? Okay. Our beta position electrons are being shared where? Between the beta and the alpha what? Carbon. The electrons in our carbonyl bond are being shared between? Which one's going to generate the larger positive? The carbonyl carbon. So our Grignard reagent almost exclusively attacks the carbonyl.
The electron in the double bond, okay, at the alpha position, will do the resonance with the carbonyl.
It can. So it does, but there's also resonance on that with those electrons with the beta position. Okay, so we can't draw electron density there. It does minimize it to a certain extent, but you're still taking electrons from a carbon to a carbon. So there isn't a whole lot of polarization with that. What happens if instead we added something like cyanide? Well, cyanide is a much more stable negative charge. Okay, so what happens is, sure, it goes ahead and it attacks our position there. But then what can it do? It can do the reverse. kick it right back out. Is there a second option that cyanide could do? It could attack that beta carbon. So it's still going to go to the carbonyl carbon first. Absolutely. That is the most positive. But that reaction is reversible with cyanide. What happens if it attacks the beta carbon? Well, I can very easily say that I could push those electrons all the way back around. What is special about this new product? It is resonance stabilized. So if I have a carbon nucleophile that is stable enough on its own, that one of those steps is reversible and the other one is now effectively not reversible because I generate a resonance stabilized intermediate, which one of those two options am I going to have the greater concentration of product in? Option 1, where it's reversible, or option 2, where it's not reversible? Option 2. How do we know it's reversible? Just like with the sodium borohydride and the lithium aluminum hydride, it comes from experiment. We just have to run it, see that that is indeed the case, and that's what we work with. Okay? So there are certain nucleophiles that are stable enough that they will attack that beta position. Those nucleophiles typically get classified as Gilman reagents, though the Gilman reagent more specifically refers to our alkyl cuprates. Okay? So we've got that added complication with it. So we can look at our overall mechanisms for this. If our nucleophile goes through and attacks our beta position, our electrons come through, we generate our enolate, which in the presence of acid does give us the enol. Our enol can tautomerize to give us the more stable carbonyl. And all of that really hinges on the fact that we have resonance stabilization in that very first step. That resonance stabilization facilitates that attack preferentially, even though we have a less electrophilic carbon. Okay, this is sometimes referred to as a 1,4 addition. Okay, as opposed to what? What's the other option? It's a hint and a new reaction down below. This one's known as a 1,2, where our nucleophile attacked our carbonyl carbon. Why do we call these 1,2 and 1,4? Interesting steps. I didn't think of that. What was that?
Carbon position.
Carbon position. What were you saying, Carlos?
Number of atoms apart.
The number of atoms apart. So looking at our positions. If we take a look at our product, okay, before we actually do the tautomerization, we added a hydrogen there and our nucleophile there, right? In our upper right hand. If we start at our oxygen being number 1, 2, 3, 4. Where did I add things in my structure? Position 1 and 4. There's my 1,4 addition. What happened with the 1,2 addition? I look to the product and see what things were added. I have the hydrogen and the nucleophile. The hydrogen's on our oxygen is position 1, 2. Where did I add things? Position 1 and 2. So I have a 1,2 addition. The 1,4 addition can sometimes be tricky, as it is in this case, because we can end up doing that tautomerization, which makes it look like a 1,2 addition happened. Okay? But you have to focus on the intermediate product, not our final tautomerization product. Okay? Questions on anything shown with those mechanisms?
Why is the oxygen coming as a 1 position?
All we're doing is just counting where our new pieces were added. Once we know where our new pieces were added, we then go through and do our chemistry. Yeah, it's not naming. It's not naming at all. Entirely separate.
These are always at acid.
They can be under base conditions as well. Okay? And even then, you would probably see that hydrogen get added to the structure to some small amount. because in all cases you will have some solvent or some acidic hydrogens somewhere in solution. It does not have to come from an acid. Yes?
Will it happen at the same time to form 1, 2, and 1, 4 products?
So that's a good question. Is it possible that a given nucleophile will react both in a 1,4 and a 1,2 addition type pathway? Yep, it is possible. Okay. Is that a very likely thing to show up on any kind of exam? Remember, we're kind of trying to set you up with the idea of trying to build things, work with synthesis. Okay. Is it a good idea to use a nucleophile that would attack in both a 1,2 and a 1,4 addition to make a single product? Why is that a really bad idea? You get 2 products. Okay? So it is possible that we can get both the 1,4 and the 1,2. Okay? But we will try and use our reagents, okay? Change the nucleophilicity of our reagents to make sure that we only get one or the other. Right, at least as best we can. Regardless, both are possibilities. Our yield does tend to drop. All right. Other questions on those? Yeah.
Which condition did you want for? Which one did you want to?
All right. When did we get the 1,4 addition? There's only one case in which we could get the 1,4 addition. There's a big hint. We just went through an example of it. The nucleophile I used was cyanide. Whoops, sorry. The nucleophile I used was our Grignard. And in the 1,4, the nucleophile I used was cyanide. What was our big difference? Reversibility. Okay. Our 1,2 is always going to be favored until we have reversibility. If our reaction is reversible, we'll get the 1,4. How do we know it's reversible? At this point, I said we're just comparing one reagent to another. Okay? So under these conditions, we would say cyanide is going to be likely to be more reversible than our Grignard, so we would expect more of the 1,4. Does that mean the 1,4 is what I get? We haven't made that statement yet. All we've said is in comparison. Okay, so a lot of organic chemistry is about this comparison. When it comes to an actual synthesis, we have to have some way to decide which one favors what. Okay? And that kind of comes out of our nucleophilicity ranking. So someone went through and started to evaluate all of these possible nucleophiles. So if we take a look at our Gilman reagent, it's our least nucleophilic. Enolates are a little bit more nucleophilic than our Gilman reagents, and our Grignards are the most nucleophilic. Okay? So if we go through and take a look at these, our most reactive nucleophiles, like the Grignards, will attack in a 1,2 addition because we're trying to neutralize that ridiculous negative as quickly and swiftly as possible. The only way we can do that is to get it to react with the most positive carbon, which will be our carbonyl. If that process is not reversible, I've now lost my nucleophile and I'm done. So I can only do the 1,2 addition. If, however, that process is reversible, meaning I have stabilized the nucleophile in some fashion, say through an enolate mechanism where there's resonance to stabilize it, then I can start to see the formation of my 1,4 products. And our enolates will tend to do that. Okay, so we'll see a shift from our 1,2 products starting to move towards our 1,4 products. Our Gilman reagents and doubly stabilized nucleophiles, okay, like our malonic ester, okay, those are stable enough that they will react primarily at the beta position only when they come in contact with these alpha-beta unsaturated carbonyls. Okay, so we get only the 1,4 additions. Okay? So yes, we've got a floating gray area in between. Okay? More than likely, you won't see any questions in the floating gray area because that becomes a difficult question to ask on any kind of exam. What you need to realize is your extremes. Your Grignards are ridiculously negative, not reversible, so you are going to primarily see the 1,2 addition. Okay? Your Gilman reagents, your copper reagents, your alkyl coppers. Okay? have been stabilized significantly enough that they will start to favor the 1,4 addition because we can do a reverse reaction for our 1,2 because our 1,2 doesn't have that resonance stabilization, whereas the 1,4 does. Okay? A bit tricky. Questions? Okay. This type of reaction, where we're attacking the beta position of an alpha-beta unsaturated carbonyl, for some reason is known as the Michael addition. Well, some guy named Michael got to attach his name to it. And it gets separated into two common kind of categories. You get Michael acceptors, that being the alpha-beta unsaturated place, because it is accepting electrons. And then you can also get Michael donors, the species that is giving those electrons up. So those are all classic examples of getting your 1,4 addition process. Okay? You'll notice that what we see within that, the lower right-hand corner, we've got our straight-up Gilman reagent. Okay? Allowing us to transfer that carbon as a nucleophile to that 4 position. We also have doubly stabilized enolates. We've got resonance both directions in all of these cases. That resonance stabilizes the negative long enough that we get some thermodynamic reversibility in the 1,2 addition. We're allowed to then have access to the 1,4 addition, and we can see the 1,4 addition actually pass through. Okay? Questions?
You're saying they'll do the 1,2 first and then they'll move to the 1,4?
Yes. What do you see as an end result, though? If you were asked to predict the product, if you're asked to predict the product of any of these reactions, which product do you use, the 1,4 or the 1,2? You'll run with the 1,4 if you have a Michael donor and a Michael acceptor. But what if you have a Grignard? A Grignard is not a Michael donor, which means you get the 1,2. Okay? I know, that's tricky. Just like the sodium borohydride and the lithium aluminum hydride, there is a line. That line is what allows us to separate and say we either get the 1,4 or the 1,2. Resonance stabilized nucleophiles, you're looking at 1,4. Nothing to stabilize the nucleophile, 1,2. Okay? Does that answer your question? You may not be happy with the answer, but that's a separate issue.
How do you get the enolates to stop at 1,2 then?
1,2 never forms an enolate.
I thought the enolates form 1,2 and 1,4.
Nope.
I
You
know
do
that.
not get an enolate in a 1,2. You only get an enolate in the 1,4. Yeah. If we back that up, maybe.
Right there.
In your 1,4, you get your enolate right there.
There's no enolate in the second reaction.
In the 1,2, there's no enolate. You cannot do resonance of that pi bond across because that carbon is sp3 hybridized. So there is no resonance stabilization for the intermediate in your 1,2 addition. In the 1,4, there is resonance to stabilize it. Okay, and that's where your enolate comes in. Where you might be confused is there's an enolate in the formation of these products, but you can also use an enolate as the nucleophile. Okay, so there's two separate conditions. Okay. Your enolate can be a nucleophile, but it also shows up as an intermediate in the 1,4 addition.
Meaning it's synthesized in the reaction.
Yeah. Okay. So if I'm right, give you time some practice. Okay, I'm noticing some confusion on the enolates, and I think this still is stemming from the idea that you guys don't like putting hydrogens on a structure. Hydrogen is small and easily to put on and take off. Okay? Just because you don't see H+ floating around doesn't mean it's not present. Okay? So it can easily pick up a hydrogen, and you will go back to the carbonyl compound. Okay? So your final answer in this case, if we clear all that off, I can actually look at this. We do it in the ugly fashion first. Oops, I moved it out of my screen. Okay. Tax the beta position, we end up with that answer. Okay. That is your Michael addition. Very similar to the ideas that you've been seeing. The big difference as far as this material goes is that you're not going to only be responsible for your Michael donors, you're now responsible for that carbon reagent, your Gilman reagents. It'll do similar chemistry, they attack that beta position. Whoops, sorry, hands. Go ahead, Simone.
Why does it form the double bond again between the oxygen and the carbon or the...
It did not form a double bond again.
It never went away.
No, it went away. There's just no double bond there. There's your final answer.
So I thought that
Where did those other electrons go? Aren't you short electrons?
So this is why I drew up that enolate issue before. Remember, it can pick up a hydrogen from solution. And that's exactly what's happening here. We cannot go to make that new pi bond or make the pi bond again, because what would the issue then be?
That one have 5 bonds.
Your carbon would have 5 bonds. So those electrons from our intermediate, we end up with this guy. Those electrons come back down, pi bond comes out, picks up H+. The result is that we have our carbonyl and just an alkane. We've lost the pi bond altogether. Okay? Does it make sense to lose a pi bond in an addition reaction? Yeah. Okay, you absolutely should be losing the pi bond. Otherwise, it wasn't an addition reaction. The atoms that were added across our pi bond end up being this carbon and this hydrogen. Right? That may look like a 1,2, but remember, you're officially picking up the hydrogen on your enol first. Okay? Shoot. You went first. Did you have the same question? Oh, good. Thank God. Other questions on that, now that I moved forward? Okay. This one I just kind of want to whip through a little bit because we've already talked about our enamines before. These also work in your conjugate addition reactions, and in fact they work even better for conjugate additions. Right? The enamine will go through and act under 1,4 addition, not a 1,2 addition. Right? And the reason being, actually I think I've got it, has to do with, oh, I'll come back here. Has to do with an issue with our nitrogen in our enamine type situation. So you should recognize these drawings from actually the exam. We've got kinetic and thermodynamic products. And if we look at an enolate, we have a thermodynamic product. And that is our primarily favored structure, whereas the other one is our kinetic. When we switch to the enamine, we get the same deal, thermodynamic and kinetic, except we favor the kinetic product, not the thermodynamic. And this is purely a steric argument. We've got some R group out here. That R group has hydrogens on it. We have some group out here that has hydrogens on it. What do those hydrogens start to do against each other? They would bump up against each other if they were forced in the same plane. In our kinetic structure, are those atoms all in the same plane? No. If we switch to our thermodynamic product, those atoms are now all forced into the same plane. They bump against each other. That disfavors the thermodynamic product. So when we look at our enamines, we see a strong favoring for our kinetic product, okay, for our nucleophile, which is nice because then I can get something added to the opposite side when I follow through any kind of electrophilic reaction or nucleophilic addition. Okay? Which those of you in lab might be panicking slightly because, yes, this is the answer to the question of why we use proline.
I saw it in one previous video, and we did that it favored the thermodynamic, where it was sterics, but you said that it was the opposite.
For the enol, maybe. We definitely went back and forth, but it's the enol. The enol is favored thermodynamics. The enamine favors kinetics. I'll tell you. We definitely talked about that. I said there was a steric hindrance.
We talked, I literally sat in our